Hi, it's Dr. J here. In this video, we will use ideas from the photoelectric effect that we covered in my last video to solve a question from the 2021 WACE paper, question 13. The photoelectric effect uses light to liberate electrons from metals. The graph of the maximum kinetic energy of these liberated electrons from the different metals plotted against the frequency of the incident light is shown below. A. Estimate the threshold frequency for the potassium from the graph above. Okay, so you may remember from my last video that the critical frequency can be obtained from the intercept on the x-axis. So if we look at potassium and we have a look at where F0 would be along here, so each of these divisions is 0.25. So it would be around about halfway between 0.25 and 0.5, so it would be about 0.37, 0.38 by 10 to the 15 hertz. So let's just write that down. Something to note is that they've told you to estimate, so you should be looking at 1 or 2 significant figures at the most, not 3. Right, the next question says, each metal has a work function that describes the minimum amount of energy required to liberate an electron from the surface of that metal. Estimate the work function for potassium from the graph above. Now, there's a couple of ways that you can do this, but the quickest way is to use the y-intercept, and it also gives us units of electron volts, so which is what the answer has asked you to find it in. So if we have a look where between -1 and -2, it's very close to that line there, so you could estimate it as being around about 1.5 electron volts. Again, only use 1 or 2 significant figures. In this case, you would need to use 2. If you were to do it the long way, you would need to use that E is equal to H times F, and you would use the frequency that you had before, but this is going to take you a longer time to do it. Okay, so probably, if you can do it the quick way, that's what to do. It then says, using your value from part B, estimate the maximum velocity of a liberated electron if light with a frequency of 1.2 by 10 to the 15 hertz shines on a potassium metal plate. Give your answer to 2 significant figures. So here they're giving you the clue of how many significant figures you should have here. Okay, so we know that the work function is 1.5 electron volts. We know also from our formula and constant sheet that the mass of an electron is 9.11 by 10 to the -31 kilograms. Right, so we know also that E light is equal to HF0 plus EK. Therefore, EK is equal to E light take away HF0, and let's write this out so that we end up with minimal calculations. So I've got H and then I've got F of the light, which is 1.2 by 10 to the 15. Take away F0, which we've got from part A. And we know H is 6.63 by 10 to the -34. Can't remember what the units are for that. Not that it matters too much, but let me have a look up what that is. So joule seconds, that's right, I thought it was. I just thought I'd check. So if we pop that through our calculator, we end up with 5.5 by 10 to the -19 joules. Now, EK is equal to 1/2 mv squared. So if we pop that in, So we've got 5.5 by 10 to the minus 19 is equal to half, and then I have 9.11 by 10 to the minus 31, and then V squared. V is equal to 1.1 by 10 to the 6 meters per second. Okay, and that's your answer there. Okay, next it says the diagram below shows how the kinetic energy of the liberated electrons is measured. The ammeter measures the photocurrent, and the battery can reverse and vary the potential difference between the metal plate and the detector. The potential is increased until the ammeter reads 0. So this is the exact setup that I addressed in my last video. So you might need to go back to that to have a little bit of revision. So it says below is a graph of photocurrent versus potential difference. On this graph, draw the resulting curve when the light of the same frequency, so that means the same energy light, but lower power. So lower power means lower intensity, okay, because it means that we've got less photons. So therefore, our curve will look something like that. So the stopping voltage is the same, and that's because the energy of the light is the same. So therefore the kinetic energy of the particles will be the same, therefore the stopping voltage will be the same. And then it'll just be lower intensity implies less photoelectrons, electrons can be generated. Okay, so that is question 13 completed. Notice that the number of marks that you've been allocated to this question is 13, and that should have taken you a lot less than 13 minutes to complete. So it's a bit of a bargain question there. In this video, we solved a question from the last year's WACE paper, the 2021 WACE paper. It was relating to the photoelectric effect. We used the ideas from my previous video to solve all of it. It was a pretty quick and easy question to solve. Thanks for listening to my video. Please subscribe to Dr. J for the latest physics tutorial. Thank you.